Before diving into the detection head, let's take a step back and review what we've achieved so far with the backbone and neck, two critical components that prepare our model for accurate detection. The backbone is where everything begins. It's responsible for analyzing the raw image and extracting meaningful patterns. Early layers focus on low-level details like edges, textures, and simple shapes, while deeper layers extract high-level semantic information, recognizing complex structures that help differentiate objects. Think of the backbone as the eyes of the model. It scans the image and builds a deep, multi-layered understanding of what's in the scene. In this YOLO11 architecture, both the SPPF and C2 PSA blocks are defined within the backbone section of the model, as seen in the official Ultralytics YAML file. This means they are treated as part of the feature extraction process, refining and enhancing the representations before passing them to the head for detection. However, it's worth noting that these blocks serve a role that could also be associated with the neck. The SPPF block, for instance, performs spatial pyramid pooling, helping to capture multi-scale features, while the C2 PSA block enhances feature interactions using a spatial attention mechanism, which helps the network focus on important regions of the image. Since both improve the quality of features rather than serving purely for feature extraction, some may interpret them as part of the neck. Ultimately, the distinction depends on how we define the transition between backbone and neck. But in this implementation, they are officially part of the backbone. Once the backbone has extracted features, the neck steps in to refine and strengthen them. It does this by merging information from multiple layers, ensuring that we get the best of both worlds. Low resolution, high semantic features, great for recognizing object categories, but lacking precise spatial details. High resolution, low semantic features, crucial for localizing objects accurately, but not as strong at distinguishing object types. Upsampling is used in the neck to refine features and merge low-level and high-level information. While it helps improve spatial resolution and enhances the detection of smaller objects, some very small objects may have already been lost earlier in the process. By intelligently combining these features, the neck improves multi-scale detection, allowing the model to detect small, medium, and large objects more effectively. It also enhances spatial and contextual information, making sure that objects are accurately classified and well localized before passing everything to the detection head. Now, I have one last thing for you, something that I believe will solidify your understanding of this powerful feature extraction architecture. This might just be the moment when everything clicks. I hope you enjoy these visualizations as much as I did, and that they drive the point home. I'll do this by showing a feature map for each stage, so you can see how the image is transformed from the input all the way to the detection heads. While we can't perfectly trace a single feature map through every stage, we can still get a strong intuition by focusing on similar feature maps. We start with our input image, which has dimensions 480 by 640, height and width. I'll highlight a bounding box around the car, so as we go deeper into the network, you can see how its spatial position remains consistent, even as the feature maps become more abstract. Additionally, I'll mark a 32 by 32 reference region, so you can track how spatial resolution decreases as we progress. All right, enough talk, let's dive in. After the first convolution, the feature map has extracted initial patterns from the image. The spatial resolution is now halved, meaning our 32 by 32 reference region is now 16 by 16 pixels. The second convolution further reduces the pixel representation. Now our square region is 8 by 8 pixels. The C3K2 compresses and refines features without changing the spatial dimensions. In stage 3, another convolution halves the resolution again. Our reference region is now 4 by 4 pixels, making it harder to recognize the car. This illustrates how the backbone extracts and combines high-level features into compact representations that still preserve essential details. Next, a C3K2 further updates the feature representation while maintaining the same resolution. In stage 5, with this fourth convolution class, the feature aggregation reaches a point where recognizing the car visually becomes challenging, though the neural network retains key features. Our 32 by 32 reference region is now just 2 by 2 pixels, a stride reduction of 16. Again, a C3K2 updates feature representation while keeping the dimensions unchanged. In stage 7, another convolution brings us to the smallest feature space of 15 by 20 pixels, where our original 32 by 32 reference region is reduced to a single pixel. At this point, the representation is highly abstract for us, but mathematically meaningful for the network. Finally, one last C3K2 concludes the backbone, producing multi-scale feature maps. Next, we move to SPPF and C2 PSA, which do not change spatial resolution, but enhance the extracted features. Then upsampling and concatenation happens. And if we jump ahead to the C3K2 in stage 13, we see that feature resolution has increased thanks to upsampling. This process continues in stage 16, further refining details. This feature will be one of our inputs to the detection head. Another convolution reduces the spatial dimension again before passing through a C3K2, which produces feature maps that are fed into the detection head. Finally, this last convolution further reduces resolution, and the final C3K2 outputs the third and final feature map for detection. This journey through the feature maps showcases how YOLO11 gradually refines and distills spatial information while preserving the essential details needed for detection. Now that the backbone has extracted rich feature maps and the neck has refined them, we're ready for the final stage,